cosmology with photometric redshift surveys. The universe has been extensively studied ever since the great astronomers discovered that we are not special. We live in an ever-expanding universe that is characterized by a set of special rules that describe how it evolves with time, called cosmological models. The currently favored model is one in which approximately 70% of the energy density of the universe is in a form only known as dark energy. We observe the effect of this energy by a combination of observations of the cosmic microwave background with either galaxy clustering or high redshift supernovae. Because the universe is dynamic, tighter constraints on the cosmological model are needed to answer some of today's most pressing cosmological questions, like: is the accelerating rate of cosmic expansion driven by Einstein's cosmological constant or some different form of dark energy? Can competing models of inflation be discriminated by accurate measurements of the shape of the primordial power spectrum of mass fluctuations? What are the properties of this dark energy? According to the standard cosmological model, measuring the linear clustering power spectrum of high redshift galaxies with sufficient precision results in the appearance of two specific features and modulations, namely the acoustic oscillations, which are sinusoidal modulations in power as a function of scale imprinted in the baryonic component before recombination, and the turnover, which is a broad maximum in clustering power on large scales originating from the radiation-dominated epoch. This paper analyzes the precision and accuracy with which currently ongoing and future surveys from the Sloan Digital Sky Survey will be able to detect these features in the galaxy power spectrum, and also assesses the resulting constraints on the currently favored cosmological model. To get the best estimates for these features, the current and future photometric and spectroscopic large-scale galaxy surveys were compared with each other. Because we want our test surveys to resemble realistic feature surveys, a large number of galaxy distributions were simulated using Monte Carlo realizations generated from a fiducial power spectrum. In generating the galaxy distributions, a similar cosmology to the currently favored model had to be assumed so that the fiducial power spectrum could be derived. Other assumptions like the area depth, which was limited to an average magnitude of 22.5, and the photometric redshift accuracy also had to be predetermined as a baseline of what feature surveys are expected to handle. For computational convenience, a flat sky approximation was used, and the resulting power spectrum from the realizations were then calculated for both the spectroscopic and photometric cases and compared against each other. But how accurate are the surveys? Results showed that the acoustic oscillations could be detected with 99.9% confidence with a large photometric survey when compared to contemporaneous spectroscopic surveys. To achieve a 3 sigma detection turnover, however, would only be possible with an accuracy of 12%. All the previous models shown here were detected using a model-independent approach when calculating the power spectrum. For lambda CDM, the cold dark matter approach, which relied on varying the shape of the parameter, 3 sigma detections were a factor of 4 times better than the model-independent method, with accuracies of the acoustic oscillations much closer to 100% than the model-independent method. In all cases, the photometric detections proved to yield convincing results that they are comparable to their spectroscopic counterparts.